So thank you for the distinguished three speakers. It's a very interesting talk about the real pilot scale of the resource recovery, AI on lithium and then critical mineral from the oil and gas produced water. So now it's time to have a more specific question from the audience. Also, if you have any other help or collaboration, so it's a good timing, we can discuss together. So, first, let me start from your presentation slide. I can start with the three of you. So, Qilin mentioned about membrane distillation and then membrane crystallizer. It looks like you are utilizing the membrane distillation. No, it's different. So, forward osmosis. So this is more about osmotic assisted reverse osmosis, right?
No, it's actually basically forward osmosis where we apply a draw solution on one side of the membrane and we apply the crystallization substance on the other. For example, as you've seen on the pictures, on one side of the membrane we have sodium chloride concentrated to about 250 to 280,000 TDS. On the other side, we're applying the magnesium chloride draw solution. Magnesium chloride is significantly higher osmotic pressure substance, and it takes out the water, and ultimately crystals start forming on the one side of the membrane. The membranes are tricellulose acid type membranes. They are not there is no thermal process involved of any kind. There is no heating. The only place where we are using basically cooling, not heating, is, as I mentioned, the draw solution. As it draws the water, it goes down in concentration. We start typically at around 380 to 400,000 TDS when the draw solution is applied. It goes down to about 280,000. And as we go through the cooling tower, we are actually, by just changing the temperature, we are reconcentrating it in a very elegant and efficient way. So there is no heat involved in any case.
All right. Because membrane distillation, so Professor Sangho Lee mentioned about third generation of the MD and then some hybrid system. So promise project. So you are not continuing the membrane distillation based on your resource recovery, or are you still considering the membrane distillation for your brine resource recovery, like Qilin's application?
No, currently we just wanted to focus on using ultra high pressure reverse osmosis and osmotically assisted reverse osmosis for non-thermal membrane-based brine concentration, because we believe that this is the way to reduce the energy consumption. Whatever membrane distillation we use, we always end up with higher energy consumption than these membrane brine concentrators. But since our project is also open to new innovations, so if we believe that some other technologies are actually better than our original plan, we'll very happy to consider the new options.
All right, thank you. So Qilin, the membrane distillation you have experience, do you have any long-term application and how this can sustain for our brine concentrate more?
I really do think that if anyone can figure out a way to reduce energy consumption would be great. And so far our multi-effect design was able to, by just the module itself without any additional recirculation or heat exchanger, can get to a goal of over 5. So just simplify the membrane module design itself. But that's still very energy intensive because it's thermal. So for the oil and gas industry, their bigger goal is actually volume reduction. Generating clean water is actually a secondary objective for them. So if there is a way to utilize the ambient environment, because the ambient environment can actually facilitate the evaporation itself, if you can incorporate that, the energy that you can draw from the ambient environment to further reduce the energy consumption for the MD process, I think that would be, any creative ideas would be greatly appreciated. I guess another thought in that aspect is the design, the similar technology, interfacial evaporation process. If you are not trying to harvest the clean water, interfacial evaporation in the state of Texas, because we have significant amount of land that's not being utilized, abundant sunlight, and that could be the most energy efficient approach. However, being a water person, I really wanted to figure out a way to harvest that clean water. If you use interfacial evaporation, the challenge is how do you collect the vapor and how do you condense the vapor using less energy?
All right, so now it's time for open to audience. Do you have any question? And then come to the microphone. Then please.
Hi, good afternoon now. My name is Diego, coming from Aruba, Nikolay. I had a question on your presentation, because on brine valorization we focus a lot on different elements and things as well. But I noticed you mentioned the possibility for cement alternatives and what is going on with the coral restoration project or this type of projects. How do you see that fitting within the whole picture, and not just putting that in the ocean, but actually for construction materials and so on? How does that fit in the overall?
The use of brine minerals for cement production is beneficial in multiple ways. At this point, obviously, this is a corrosive substance, so as a result, if you do have rebar-based systems, those rebar-based systems have to be designed with special steel to prevent corrosion. So at this point, most of the structures we've done have been structures without any rebar in them, so those are architectural or coral reef-based systems. We're currently working on changing both the rebars and also the actual chemistry of the brine concrete to be able to start building rebar-based, supported structures that can carry very high loads. So that's the next step of our research. It is possible. It's a matter also of cost and applications. In NEOM, we do a huge amount of construction. About a quarter of the world's steel produced today is going into one of our projects. So as you can imagine, we do have a lot of cement and concrete involved. So it will be a valuable contribution to the industry. But it's not the main amount, because the amounts used are fairly small compared to the amount of salts being produced. A 100,000 plant will produce about as much salt as a average size pyramid. So that's a lot of pyramids if you think about the number of plants we have.
Okay, please.
Hello everyone, I'm Omar from the University of Oxford, and my question for Mr. Nikolay regarding the concrete. Now, do you use it as slurry in its wet form, or did you think about using it as a powder? And also, did you think about accelerated carbonation or more like ambient curing?
We're using it in a form of slurry. We're using 3D printing, so we're preparing a slurry and then a 3D printer that actually prints those shapes that I showed you on the pictures. So it is 3D based printing that we found is the most cost-effective way to go. We programmed it, and we have made all kinds of mainly architectural components, using this to print also benches and other components that are functional, but without the ability to carry heavy weights. So chemistry-wise, we only have applied this in slurry. We have not created a powder application.
And finally, do you use like accelerated carbonation, or do you think there is a use for more ambient type of curing?
Yeah, we're not using accelerated carbonation. The process of making the concrete doesn't vary significantly from conventional making of concrete. So the process is fairly standard. It's the constituents that are included in the mineral constituents are what's really the valuable component of what we do. Our technology otherwise doesn't change the production process.
Okay, thank you. One last question for Professor Lee, and that's regarding your models. Do you see it as easier to integrate them with already existing, let's say, systems, like how many billions of parameters that is needed for the software in this case, or your data system?
So let me get your question a little bit specific. I mean, so can you repeat a little bit more?
Yeah, like for your language models.
Okay, yes.
Yes. So when you use them, how many parameters you are incorporating in the systems, like to make it viable? Like
Yeah, actually, we are working on this topic from like less than 6 months ago. So we are still working on determining the parameters required for this language model. But one thing that we are considering is that we wanted to make this model as small as possible, because people are frankly talking about the energy consumption by this generative AI. So we just wanted to have a small but larger language model. But at the same time, we needed to make it domain specific. So with this concept, we will limit the number of these parameters. And we are going to start from some base model, and we will add some new noise and new variables and new information to these language models. So we are not starting from the scratch. Instead, we will make this model, and we will also reflect the outcomes from our project to make this model more domain specific.
thank you very much.
So next, yeah. So in the meantime, Professor Lee, so when you have achieved your AI model after 5-year project, how much energy consumption you expecting to reduce from your AI control?
So you mean like
Energy consumption, like you want to save the cost, right? Let's say energy or cost, how much you can reduce overall after 5 years?
So using AI model, basically we wanted to reduce at least 20 to 30% of energy consumption by design and the operation optimization. And in order to do that, we will need to use AI models, and this will also use some energy. But based on our preliminary calculation, although we needed to call these AI models frequently, we will have more gains of energy reduction rather than energy consumption by AI models. So we'll have net energy reduction using these AI models.
Hello, yeah, I'm Shantanu. I'm from University of Texas. I mean, either of the panelists can answer my question. I actually have 2 questions. Firstly, typical extraction of mineral from hypersaline brines involves, you have to reach concentrations close to the saturation limit at least. So one issue with going that high in concentration is that you have a lot of scaling and other detrimental issues that can happen either in thermal or membrane-based desalination. So are either of your models incorporating that, or if so, if they are incorporating in the future, then what are the plans for that? So that's my first question. And the second question is, after you bring it up to the saturation limit, from what I understand, you have to send it redirected to a brine crystallizer where you actually crystallize the mineral out. So is the brine crystallizer also being modeled, or are the models as of now focusing only on the tertiary dewatering part? So, yeah.
So is this to my?
I mean, either of you.
You know, it's a little bit.
Give it to Chile.
Okay, so
Well, he was asking about modeling, but in the extraction process, so right now the industry standard is you obtain a clean brine first. You don't necessarily have to precipitate out the crystal. And then that brine is then refined to give you the crystal, and of course that involves sending it to crystallizer. But the brine extraction process, at least the way we're approaching, the traditional approach is exactly what you're saying. You add chemical, you precipitate out, and so you have a lot of scale formation in the system. And at the same time, you also lose your target mineral because it co-precipitate with other scale, chemical scale. That's why we choose to use electrodialysis, because this allows us to produce a clean brine, and you can concentrate that brine, but not necessarily to the saturation level.
Okay.
let me just answer about the models. And in fact, in our Promise project, our target is the 80% recovery. So this is actually part from these hypersaline conditions that we are talking about.
So this is 80% recovery for seawater or for brine?
Yes, seawater, the 80% from seawater. So it will be about 180,000 milligram per liter of brine concentration or more. But even with these kind of conditions, we also anticipate the scaling problems, and of course we will develop some nonlinear AI-based scale prediction models so that we can just make this operation stable.
Looking forward to that. Thank you.
Hello everyone, this is Jinghua from Clemson University. Jing like Jinghua, more easy to remember. Currently we are working on desalination technology for agriculture purpose. So we were interested in nutrients. So the selective membrane are very interesting to us. So I'm curious about the selective membrane Dr. Lee could develop. Usually, like based on your understanding, developing a membrane, how to the real product, how long will it take to become a real product? And I'm also curious, like for current, like a critical project for the selective membrane, will it be possible to kind of directly cooperate with the academia professor? And like I want to know like how this selective membrane really used in the industry point of view, and from the develop to really use it, and how long it take as well from the first like industry point of view and from academia point of view, and also what's the main gap to let it become the commercial product.
Yeah, selective membranes have, the concept of selective membranes was created about 3.5 years ago. So between then and the first prototypes, which are 2.5-inch elements of potassium chloride selective membranes, it took us about 2 years to create those. The key component to any of the selective membranes is active material that is used in ion exchange resins. If you think about ion exchange resin, there is an ion exchange support in a tiny substances called ionophores, which are complex molecules, organic molecules, which are designed to allow only a particular substance to go through, and then the others are rejected. The way we were able to achieve the rejections, we were able to achieve about 85 to 95% rejection in letting a particular mineral to pass. And that was possible by having multiple layers of ionophores, one above the other, because if we just have one layer on a conventional membrane, we achieve about 30 to 40% passage. We are using 7 layers to achieve 85 to 90% passage. And those are macro layers that are put on the membrane one after the other. Once we get to that point, we currently actually testing 2.5-inch elements with potassium selective membranes to verify over a long period of time their ability to sustain selectivity. The principle of what we're using can be applied to technically almost any mineral. As long as we can extract it by ion exchange, that means that the ionophores already exist. The ionophores that we are using for our membranes is actually a commercial product, which is not patented. So anyone can use it to make the selective membranes themselves. The one huge benefit of selective membranes is they dramatically reduce the transmembrane pressure. So for example, one of the answers of how do you get from 2.27, which was the SWCC record of energy, to below 2, is if we use selective membranes, the transmembrane pressure goes from about 20 to 24 bars down to 12 bars. 12 bars is over 20% reduction of energy, so 2.27 becomes less than 2. That type of possibility exists for any of those because the benefit of that energy reduction comes from creating technically molecular paths for the water and the mineral to go. The way the system works is both water and the particular mineral we're selecting goes through the membrane, so it goes on the permeate side, on the clean side of the membrane. Now we have a mix of clear water and the mineral. The water then goes, this mix goes through the second stage of the system. That's usually brackish water arrow membrane. And that brackish water arrow membrane is conventional membrane. So as any other conventional membrane will do, it will separate the salt from the water. So we end up still producing drinking water, and all the particular mineral, like in our case potassium chloride, as I gave an example, stays in the brine. And there are 2 stages in a conventional brackish water, second stage brackish water arrow facility. So we end up with concentrating it and recovering about 85% of the total amount of mineral that was initially in seawater directly without increasing the energy, actually surprisingly by decreasing the total energy of production of water and producing that mineral at the same time. The cost of production of the membrane, we're currently commercializing the product. We're working closely to create commercial products, I should say, or commercializing the product with DuPont. So DuPont is using and testing the system, and we're working on 4 membrane elements: lithium, potassium, magnesium, and rubidium. Those would be selective membranes for production of those 4 substances. Commercialization itself, based on our discussions with DuPont, will take about 2.5 to 3 years before those membranes are actually available as commercial products guaranteed by DuPont on the market.
Thank you.
How about Qilin from the academic
I
perspective?
guess I'll share our experience and lessons learned also. I guess that's the reason why we choose the thin film composite structure is because you want to, when you start thinking about designing a membrane, you wanted to make sure that it's manufacturable, right? If you come up with a protocol that's very difficult to scale up and the industry currently doesn't have a way to make it, and then it's going to be, the process of commercialization is going to be very, very long. But the lesson learned is that, okay, even though the thin film composite structure in theory is very similar to the reverse osmosis, what we didn't realize is how critical that substrate layer is. And we thought, you have a microporous layer, provide mechanical structure, how difficult is that? Currently, every manufacturer has their own substrate, let's say form a partnership with you, they'll not tell you what the exact substrate they use. And in our case, we are not using the non-woven. We just have the polysulfone or polyethersulfone layer, and that poses a major challenge in their fabrication because their current production process requires that strong mechanical strength provided by the non-woven. It was adequate for us to make it in the lab without the non-woven, but when you go to the rotary production, that becomes a problem. So I guess my lessons learned is you got to start talking to the manufacturers early on.
Thank you. Appreciate for your detailed answer.
Thank you. Please, next.
Yes. Hello. My name is Felipe Torres. I come from Australian National University. And my research group developed an all-liquid thermal brine concentration method called multi-channel thermal diffusion. And we're excited about this technology because it's membraneless and no evaporation, and it's targeting what we think is the Achilles heel of brine valorization, which is brine concentration when your feed is above 200,000 ppm. So my question is, I have two questions actually, one from Nikolay concerning his membrane crystallizer. I saw that you had improved feeds between 300 and 350 ppt. What was the lowest concentration you've tried for those feeds? Have you tried anything like 200 ppt or so, and what's the energy consumption for that?
Yes, the higher the concentration, the faster the process. So there is a direct relationship between the concentration of the brine that we feed and the actually flux of the membrane. So if we operate at 250 to 280, the flux doubles compared to 200,000. We have done 200,000 as well because salinity could vary for various applications. Just to give you a sense of how quickly we're creating the first crystals and beginning crystallization process. If we had 280,000 TDS, it takes about 15 to 20 minutes. We start creating crystals and we're in continuous production of crystals. If we had 200,000, it takes about 4 hours. So the flux that we have to apply drops in half. That means that the system becomes much bigger in size. That's why we're striving to maximize the concentration of the feed. And it becomes more important than thermal systems, because in thermal systems, every thermal crystallizer has a pre-evaporation component. So even if we put it at 200 to 250 to 280, the pre-evaporation component always will bring it to 320, and then put it into the crystallization process and then crystallize it. In membrane crystallizers, we don't have any pre-concentration. It just goes through the membrane and affects the flux.
I see. In a follow-up question, have you done like scaling, fouling, long-term testing for those membrane crystallizers?
Yeah, we've been running the crystallizers for there's only one crystallizer, I should say, not crystallizers, but we tested different membranes in different substances, but using the same exact membrane that you've seen on the picture. We've been testing for at least 6 months, I would say, on sodium chloride, because that's our main product. And on the other products that I mentioned, calcium salt carbonate, for example, we've been testing shorter. Potassium chloride, we've tested also about 2 months. The overall process is very reliable, and the loss of magnesium chloride that we get through a little bit of evaporation and through the column is fairly easily compensated by the magnesium selective membrane, which provides us with new magnesium chloride directly extracted from seawater. So basically that allows us to get to the point of zero chemical being purchased out of the system. The magnesium chloride is produced directly from seawater by selective membrane for magnesium chloride.
Okay, so thank you. And just a question for Qilin Li, Professor Qilin Li. I had a question concerning your membrane distillizers. In one of your figures, you had, like, they go up to concentrations of 200,000 ppm. Have you tested for higher concentrations, and how do they behave?
250,000 is the highest we've tested, and that's our feed. concentration. So we haven't, for sodium chloride, we haven't tested all the way up to crystallization, but for other minerals, yes. As I said, these HBN coating is extremely resistant to attachment by mineral crystals. So we do see accumulation of crystals on the membrane surface, but not on the HBN surface. So you can actually wash off pretty easily. But again, those are all laboratory scale testing and relatively short term. So we don't know if you, the longest we test is only a few weeks. We don't know, if you run it all year around, whether they will eventually start to accumulate on the surface.
Nice. Thank you very much.
Thank you. So, we have.
I thought it would be nice to switch sides for a moment. I'm Marc Philibert. I'm with Suez. I have a couple questions in terms of sort of practicalities for market, right? First of all, you mentioned like there's potentially more in the oceans than terrestrial mine, but for that to become a reality, then you have to make sure that you're producing it at a lower cost than the terrestrial brines. You mentioned that Mr. Voutchkov, you mentioned that that's the case, but we don't have any numbers. Is that the case for all the minerals? Do you have numbers that show that brine mining from the ocean is cheaper than mining from terrestrial mines?
There was a graph with, there was a graph with dots. There was a dashed line and black dots and white dots. The black dots are all minerals that we today, with the technologies we know and have, cannot be competitive. The white dots that are above the dashed line graph are all minerals that we actually can produce with the current existing methods of production. We can produce it more competitively than terrestrial mining. So that graph basically shows we have about a third of the minerals that are of value, our technologies exist for them. The rest, you guys here have to figure it out. So you're the scientists. But the reality is there is a great opportunity to make those other minerals possible to harvest as well. It becomes a matter of how much is it, just to give you a sense. 100,000 cubic meters a day plant contains gold, but the total amount of gold, if you extract it with 90% recovery, because technically nothing can be extracted at 100% recovery, that will be about 5 kilos. It's certainly not worthwhile. Not at today's markets of gold. Maybe, if gold goes 10 times higher in price, they will at one point or another. So there are really two important issues: the price of the mineral on the markets and the cost of production. So as you noticed on the graph, and I can share it with you if you're interested, there is still a lot of work to be done for many of the minerals.
I mean, I've seen that graph before, but the way I interpreted it was, okay, we're able to, our cost, mining it from the ocean is less expensive than how much you get from the revenue. However, that didn't necessarily mean to me that it was cheaper to do it from ocean brine mining than from actual terrestrial brines, because they might be still even more efficient and cheaper. But that's fine.
Yeah, this is based on the numbers that you see on that graph are based on commercial values of the minerals that are available on the market. When we create the value, this graph, we look at how much we can produce the mineral for, and what is the value for that mineral on the market. And the market value is established by terrestrial mining, as you know. It's not established by seawater. Seawater brine mining is in its beginning. So the information we have on the terrestrial markets are the market values that we see today.
That's fair.
So that's how we compare, and that's how this graph was established.
I have a follow-up question to that. The other issue with market, and I think Dr. Lee sort of mentioned that at some point, is that, for example, NaCl, we know if we were to produce the NaCl that we have in one of the huge plants, we produce more NaCl than is sold globally. So you're gonna overflow the market with something you cannot sell. the same thing could have been said with the lithium for your brines, where you said you have 3 times the amount that's being sold in the US. So my question is, what are really the minerals that we can find? What's the level? Because brine mining, ocean desal, if one plant is able to produce enough NaCl for the world, it's not going to be very interesting for everyone.
Yeah.
So do you have any conclusions as to which are the minerals and where, you know, the limits are?
Yeah, I mean, there's always limits to everything, as you pointed out. If all those desalination plants have a brine mining facility that makes salt, we'll flood the markets, the world markets with salt. And in that case, we can compete with terrestrial markets only if our cost is significantly lower. And that's why I gave you an example of solar salt, because most of the markets for salt today are based on solar evaporation ponds that make them. Those ponds, the cost, the sales price of those from terrestrial sources, obviously, is about $25 a ton. That's what you would buy it from. And it's only at 96% purity. The cost of production, considering membrane crystallization that we have today, is $18 a ton. So realistically, we can compete even with lower quality markets, but $18 a ton from 99.6% purity. As far as the demand for it, as we know, the world is moving away from oil, and therefore there will be surplus of oil in the Middle East, which, with the salt available, would, result in higher productivity of plastics. And you would say plastics are really not a good thing because they may impact the environment, as we've seen it impacting the oceans and others. That's why the Saudi government is investing in a huge program, which you've never heard of, jointly with the US, is to create plastics that are made, as I explained, from these 2 materials, but plastics that are regenerative. What that means is you have a piece of plastic, you grind it in chips, and you use these chips to print other component or the same component. Currently, the technology we have available today is you could reprint that piece, turn it into chips and reprint it 10 times. With regenerative plastics, the demand for plastics will increase dramatically because we can actually replace almost everything. So the Saudis look at the future as the moving from Iron Age into Plastic Age. And Plastic Age will require a tremendous amount of oil and salt. So that's how they see oil and salt moving in the future. So they are investing in these technologies because of the longer view of where they'd like to be.
Okay, thank you very much.
Just one thing that I want to briefly mention here about the economic feasibility, and as far as I know, economic feasibility depends on whether the actual consumer exists or not. And so if the demand exists, it will have economic feasibility, and demands actually depends on the quantity and the purity. And in our Promise project, we aims at economic resource recovery, which means that we are first looking for the consumers, possible potential consumers, who are willing to purchase a certain amount of brine, salts or products from the brine, and we just specify. We just know about the specification and purity and actual amount of these needs for the amounts, and based on that we can develop the technology, and this will make this brine mining more economically feasible. And at the same time, we are also developing some technologies which are not currently economically feasible. But the reason why we are doing is, as you already mentioned, we don't know about the future price changes. So sometimes some minerals, which is economically feasible right now, but in the future they may not be. And there are also some minerals which are not currently economically feasible, but we don't know about the future. So we just want to be ready to have technologies for the future changes, and this is the approach that we are actually taking.
Thank you.
Thank you. So we have a lot of experts in this room. So I just want to pick up two people and have a brief perspective of brine resource recovery and AI. So first person is Professor Miriam Balaban, and second person will be Professor S.K. Hall. So let him SK start first, and then I will go to you, Professor Miriam Balaban. Just overall your perspective of brine resource recovery and AI. How do you feel like based on your experience? Please, SK Hall, can you come and share your perspective of brine resource recovery AI? 2 minutes.
2 minutes. Hello everyone, I'm S.K. Hong. I'm a professor at Korea University. I didn't expect he's going to ask that question. But I have a keynote speech on Wednesday regarding industrial wastewater or achieving circular economy in industrial water treatment. I think the technology that we are developing for brine management in seawater desalination could be a key technology for achieving circular economy in industrial water treatment. And recently I'm working with Samsung, electronics, as well as battery industry in Korea. I mean, in Korea now the high-tech industry requires lots of water, as well as they try to recover some of the valuable materials from their industrial process. For example, battery industry, they try to recover lithium and cobalt, nickel, and all those metals. And also semiconductor industry, they try to recover some of the acid that they are using them. And so by hearing all this new technology development in seawater desalination, and also are involved in those development as well, I think we can apply this one to other high-tech industry, and then in that case, we're talking about feasibility of economics of recovering all those valuable materials. Maybe those industry, high-tech industry, economic feasibility is much better for our technology. That's my comment. 2 minutes, right? Okay, see you at on Wednesday in my talk. I'm going to talk about technology over there.
Thank you, Professor Hong. So his talk will cover continuation of the resource recovery. Now is time for our mother of desalination. So she will share her perspective on brine resource recovery and AI. So I cannot. This one, right?
In my years of editing desalination and water treatment, brine was considered a waste. And then suddenly, not many years ago, very recently, it became a value. And first of all, then we have these sessions, this work that's going on. Suddenly, it's not too long ago, it's just a few years ago. And also, so brine became a value. And then also the European Union assigned a project, C for Value, of which I was a participant. And we also studied all these wonderful possibilities of using brine and of the value of brine. So this is really what I have seen. And we continue to get more and more papers and see all the people who are now involved.
Thank you, Professor Miriam Balaban. So, anybody I'd like to share about your strong perspective of brine resource recovery or AI? Just 1 minute. Noradi. 1 minute.
Making a lot of people in trouble. Okay, let's go AI.
That's fine.
My friend.
Yes.
So I was very actually surprised that you mentioned that AI is future generation of desalination. AI is the future, yes, but what's the link with desalination? I mean, we will modernize desalination, we will make a lot of optimization, but I was expecting next generation is about technology, not, I mean, desalination technology, how to go into a new membrane or new other process. So why did you call AI as a new generation instead of saying like some, it's a tool actually to, we will get a lot of good things. Optimization is one, prediction, early prediction, fouling, etc. But why you call it next generation of desalination?
I expected some kind of perspective, but he actually asked a question, so a lot of surprise. Yes, that's a very good question. Actually, as briefly mentioned in my presentation, desalination process is becoming more and more complex. So previously, it's something that's a little bit formal, but now we are facing new challenges and new problems. And of course, the brine mining will add more complicated problems and situations. And of course, we can do without AI, and AI is a tool, but we can do better with AI. This is, if we have very good tools, why don't we just use these tools? And as mentioned earlier, we can save a lot of time, we can improve the efficiency, and we can make it easier. So this is why AI is inevitable, probably in the future for the desalination. And another thing that we have to consider is we have developed new pumps, new ELDs, new membranes, and new processes, but it's coming to some kind of limitations. How can we further improve the hardwares? When we improve the hardwares, at the same time, we also have to improve the softwares. And AI is one of those kind of softwares that can utilize the full performance of the current hardwares, but we can actually have better performances without spending smaller amount of money. And that's my perspective on using AI for desalination.
I can still give you perspective. So, 30 seconds for perspective. I remember Professor Dior, first time he was in our committee, long time, like 5-6 years ago, when he said desalinated water will become byproduct. I mean, and this is what we heard today from Voutchkov. The second thing is that we all thought that sodium chloride is actually not that good value or high value. We have huge amounts of sodium chloride and we cannot even sell it. Today I hear that sodium chloride with the oil we can replace a lot of things, and actually which is the one of the directions for resource recovery. Because if we go back to lithium, we work with lithium, including imported water from Saudi Arabia. We all know that the concentration of lithium in seawater and in brine is very low, 0.2 ppm, 0.4 ppm. It's very hard to make it economically feasible. The best thing we can get from produced water is 200 ppm, maybe 500 ppm. In produced water, which is a very challenging feed water stream with a lot of other challenging stuff. So it's difficult to make it also economically feasible. So now the main challenge for the resource recovery from brines is actually how to make it economically feasible. Sodium chloride is one of the good news because we have plenty and it's much easier to get, and if we have a market, because at the beginning we in Saudi Arabia said who will take this sodium chloride? Nobody will, there is no taker, it's very cheap and huge volumes, but actually there are some applications. So that's strategy behind. So let's push forward on this topic. Don't be discouraged because the economical feasibility is very tough compared to other conventional processes.
So what's the strategy for the existing market of sodium chloride and then brine sodium chloride? Can you share your strategy from Saudi Arabia, even
Yeah,
Qatar?
as I mentioned, the strategy is to increase dramatically the use of sodium chloride because of the production of plastics. And that is only possible if we actually have plastics that are possible to regenerate and recycle multiple times. Once that is possible, that will dramatically increase the demand for it. That's one side. The other side is the quality of the plastic products. It's not a huge secret to say that the latest models of US fighters are actually plastic. They're composite plastics. They're not steel, as you may think they would be. And currently we're using technology that I explained to deal with logistics. As you can imagine, if I have a spare part I have to ship from the US, half the way around the world, that will take me usually at least 6 to 8 hours, even with the fastest planes. Well, now you have a way of printing that component on site in a matter of hour or less than that. That is going to regenerative ability of plastics to be regenerated and reused this way, locally, in your site, beats many of the logistics challenges that we've seen. It basically defies borders. You need a spare part for a pump. You don't have to wait for 6 months as we do in Saudi often. You just get the software, you print it at your home. Or you can have a scanner that can actually make a scanned copy of what you wanted to do and print it. And that's in a matter of hours, not a matter of 6 months. That will change dramatically environment as well. We no longer are shipping, we no longer are flying planes, spending fuel on that direction. So that's why I do believe that the strategic approach of producing regenerative plastics at low cost would change the world, the demand for plastics and therefore demand for salt. So I think that's what both US and Saudi Arabia do believe will happen.
Thank you for sharing.
I just want to briefly mention one thing about this economic feasibility of brine mining. And one way that we are looking at is the carbon capture, because since climate change is becoming worse and worse, and the carbon credit will become more expensive, and since mineral carbonization the carbon mineralization is one of the very good methods for carbon capture. So if we can just look for going for this way, we'll have another benefit, the revenue created from brine mining.
All right, thank you very much for the very valuable discussion together. So we don't have time, so you can you have to do after this session. Please, you can have a personal discussion together. We have to go next step. So next step is so what we need go for next step. So industry perspective, academic perspective, also some of the oil and produced water. So what's the major? One. The most challenging problem you have, and then what you can do next step. Potentially we have a collaborator, so potentially you need some other specific technology development or policy development. So please, only one most challenging barrier, and then what you can do next step. Can you please share?
Yeah, the next barrier to break is basically creating integrated desalination and brine mining systems, which are designed around the brine mining component. First, in order to do that, to me the main component or the main field of research will be multifunctional membranes. For the last 50 years, membranes have been doing only one thing. Think about nature. Our cells, or anybody's living creature's cells, do not do only one thing. They are multifunctional. So for us to be able to optimize that benefit between producing water and salt, we do have to use multifunctional membranes. And as I mentioned, in our case, the solution that we did see is the selective membranes that allow us also to, if a mineral expires, it's no longer interesting for the industry to replace those membranes into the same reverse osmosis system with others that are focused on something else. Flexibility and multifunctionality. Those are very key.
Thank you. Flexibility and the multifunctionality of membranes. Yes, that's great. Yes.
I will talk about in terms of this brine mining and AI with brine mining. In the academic the point of view, many people have actually studied brine mining and brine resource recovery, and many new materials and new techniques have developed, but it's very questionable how many technologies can be actually accepted by industry. So it's very good to carry out some works for submitting the papers in high-level journals, but at the same time, it's also very important to make this actually happen in real-life situations. So in the academic sectors, we needed to actually develop the technologies that may be also useful in industrial sectors. So there should be a link between this academia and industry, and this is one thing that we needed to do for the brine mining in academic sectors. And as for the AI with the brine mining, in fact, there's a limited available data that makes really difficult to apply AI for brine minings. So there should be some platform to share the data and share the result, so that we can facilitate this kind of research works. And we hope that Promise project can be one of them, but we can create another platforms and conferences and workshops to make sure that we can have enough data and enough models, and they can be shared and they can be used to have some meaningful results for brine mining. That's all.
Thank you.
I was going to say multifunctional membranes, but since Nikolay already said that, I'm going to say something different. I think we really need to accelerate commercialization of innovation that come out of academic labs. There's so much knowledge in this room on desalination and brine management. But if you look at the industrial wastewater side, for example, I'll go back to produced water. This industry is actually willing to pay a lot more on desalinating their wastewater, right? Right now, their benchmark is $10 to $15 per cubic meter of that wastewater desalinated, which is, to us, would be, for those of you who work on seawater desalination, that's a very, very high price tag. But their challenge is, even though they're willing to pay more, there are no commercially available, mature, and proven technologies out there. And they're a very conservative industry. So what I'm trying to say is we wanted to see more of the industry partners jump in, be the early adopters, and help de-risking new technologies faster. There's so many bright, brilliant ideas coming out of the research lab, and not all of them will become commercially viable technology, but we need people to help us de-risk them and figure out which ones will never work, which ones will have the potential, so that we can accelerate that commercialization process.
Thank you for the wonderful comment. Just to summarize the key point for the three main speakers. So we need to have more flexible and multifunctional membrane for integrate the desalination, which will lead to our desalination translation opportunities, as well as some of the new AI-related data collection, which will give a more future collaboration. And finally, we need to have a more resilient adaptability of this commercialization opportunity between industry and academia, so how we can work together to make this opportunity, research and industry to have a good collaboration. So that's the key message we have from our distinguished speakers. And thank you for your attention. And then we'd like to continue this brine workshop for the next this 2027. This is a biannual conference which will be held in Shanghai next 2027. So please continue to work together. And before that, we want to have a special issue for this 2025. So you can submit any kind of topic, also brine, AI, membrane, any of the translation opportunity. So if you have any good idea today from this brine workshop, so you can make 2 pages of communication, maybe long review paper, even very specific perspective paper, research paper. So please, you can submit. It's already open for the tab of the desalination submission journal. So next step, you need to write, continue to engage. So looking forward to seeing you for the next this 2027. We will continue for this workshop, and then let's thanking to our 3 distinguished professors for the. So we have time. So we have.
I just wanted to add one thing. On the last day, the 19th, we do have a brine mining session in the morning. So if you're interested to hear more about brine mining, more specific technologies and details, check your schedules. 19th in the morning, brine mining session.
Absolutely, you can have a more specific. Thank you for your attention, and looking forward to continuing discussing during this conference. Thank you very much.